Hello. Today we're working on section 4.4 of the notes in BC Calculus. Now today, I'll probably need somebody sitting right over there by the computer to be able to pause quite frequently because I have all my work already shown, and so after the initial setup, all the computational stuff, if you want to write all that down, you'll need to pause so everybody in the class has time to write that down. And I just didn't want to take the time to do that while I recorded. So if I look at this, what are we doing today? Today is a fundamental theorem of calculus. So it's kind of like what we need to do in order to find a definite integral. Now if you look here, the left side of this equation, so if you're looking over here on this side of the equation, this is the same except for the a and the b. On these particular equations, we're not going to have plus c's at the end because we're going to be finding our definite integrals. And the way we do that is we do our antiderivative like what we did normally, and then what we're going to do is evaluate that antiderivative first at b, and then we're going to subtract from that our antiderivative evaluated at a. So we're going to be doing f of b minus f of a. Now notice those are capital F's, which means we found the derivative there. Okay? So here's my little hidden screen. Here's example 1. That's what it looks like. The integral from 5 to 2, or from 2 to 5, of negative 3x plus 5 dx. And the way that I look at that is this right here I do my antiderivative. And the part I have circled in red is my antiderivative. So I have negative 3x squared over 2 plus 4x. Now there's two ways you can do this over here on the left side. I've seen it both ways, where you can just do a straight line and evaluate it from 5 to 2, or you can do like put the little bars on it like that to include all that. Now actually you're evaluating from 2 to 5. You go from the lowest to the highest when you evaluate that. But I have found that students find that confusing, so when I talk about this, I'll always talk about going from 5 to 2 to remind you to plug in the 5 first, and then you plug in the 2. So I take my antiderivative, and what I did on the left side, I have negative 3 times 5 squared divided by 2 plus 4 times 5. And I put that in brackets to emphasize that all of this right here, this part of my bracket was when I substituted in my 5. Minus, now I substitute in my 2. And I put brackets around everything substituting in 2 to make sure I don't mess up on my computational part of the problem. So I plug in a 2, so I get negative 3 times 2 squared, which is 4, divided by 2, plus 4 times 2, which is 8. Now this is where you might need to pause. Let me just get rid of the rest of that. Then I just evaluate the first parenthesis and the second parenthesis, and then I get negative 39 over 2. So if you need to pause that, that is the final answer for example number 1. Now, if you want to, I would like for you to pause and try example 2 on your own, and then when you're done, just kind of let the person running the mouse on the computer know so you can see the final answer. So I have for my final answer on example 2, I got a final answer of 0. All right, here we go again. I don't know. Are we on example 2? I don't think I hit that earlier. So example 2, is everybody okay with 0 as a final answer? Okay, moving on to the next ones. The next problem is number 3, and it looks ugly, you know, the integrand there. So what I'm going to do is when I just see one term in the denominator, I'm not going to do the quotient rule. I'm sorry, what am I thinking? That's a derivative. We have to somehow get that up to the numerator. But I'm not going to bring it up to the numerator and then distribute. What I'm going to do is split it up. So I can do basically the antiderivative of each one of those terms. So when you have one term in the denominator, when you're trying to find the integral, think about splitting it up into two separate fractions. And that's what it looks like. Bring everything to the numerator so that I can evaluate it. So I have 1/2 x to the 2/3 minus 1/2 x to the 5/3 as my integrand. Now remember, this right here is x to the first. I'm looking at this equation right here. So I have x to the first and x to the third in the denominator. So you remember, you take the numerator exponent minus the denominator exponent. So that's how I get my x to the 2/3. And the same thing with that, I have x squared and x to the 1/3, so I subtract exponents. Alright, so here you go. I'm going to show you all my work here at one time. I do my antiderivative, so I'm looking at the step right here with the, let's get some happy faces right here. Happy face line right there, that is my antiderivatives, and I'm ready to evaluate from -8 to -1, typing or plugging in the top number first. So if I plug in a -1 there, and then, oh, that would be a, wait, let me look at that. Yeah, that is positive. I don't know why I changed that. So I have 3/10 times -1 minus a 3/8. When I take a -1, I plug it in, raise it to the 8/3 power, it will be positive. So let's make sure that that's a 1. The messy part is sitting here and trying to evaluate all this. And again, please emphasize the fact that right here is plugging in the -1. That's the first set of brackets. Second set of brackets is when I plug in the -8. And then I got a final answer of 4569 over 80, which is about 57.113. Okay? Now those are pretty much basic fundamental theorem of calculus problems, just finding the integrals, the definite integral. Now where it gets a little bit complicated is when you get into the next example, which has an absolute value in it. I have the integral from 0 to 4 of the absolute value of x squared minus 4x plus 3. I'm doing this with respect to x. When you look at that, you have to think about our absolute value. So I'm going to take time out here and reevaluate or reemphasize this absolute value. If I have x squared minus 4x plus 3, let me see if I did it up here. I'm thinking about factoring that x squared minus 4x plus 3, and that is x minus 3 and x minus 1. Now when I think about this, I need to evaluate, when we do this antiderivative, to find the definite integral, we're looking at the area between the curve and the x-axis. Now what happens here is I need to make sure that all these are positives. So when I look at this, I am looking at my first derivative. When you think about it, your first derivative is the integrand part, okay, right there. If that is negative, don't I know that I have some of my graph below the x-axis? So if I look at this, this is my integrand, x minus 3, x minus 1. I look there, and I have positive values between 0 and 1 and 3 to 4. And I have negative values between 1 and 3. So what I do is, when I'm taking the absolute value of this, I'm looking at between the intervals of 0 and 1 and 3 and 4. I know, and why am I using only up to 4? Oh, maybe I need to address that issue. I'm looking right here. I'm going from 0 to 4. So I know between 0 and 1, and then again from 3 to 4, my integrand here is positive. But if it's below 3, so between 1 and 3, I know that it's going to dip down to the below the x-axis, and that means it's going to be negative. So to take the absolute value of that, I'm going to have a an opposite value of that. Now I was trying to sketch here, and I can't sketch and talk at the same time. This graph here is finding the area between the curve and the x-axis, as well as down here, as well as up here. So basically, when I go to do absolute value of that, this right here, if I take away those absolute values, that would be coming in as a negative value. So actually what it is, let me draw it in green. Let's see if I can find green. Actually, if I take the absolute value of that, I need this part up here. Okay, so I need to flip. Boy, that's not symmetric at all. But you get the idea that this part right here, if I take the absolute value of that, it's going to flip it up here. So when I go to evaluate my integral, when I take off that absolute value, I have to address that issue. We can't take an integral or an antiderivative of an absolute value. We have to remove the absolute value. So here's the kicker. Right here I have to split up my integral from 0 to 1, bingo, the same. And then from 1 to 3, notice I had to plug in that negative from 1 to 3. Okay, because if I go to take the absolute value of that, I need to make sure it's positive. If I don't take the opposite of that, I'm looking down there, and it would be in the wrong part of the wrong side of the x-axis. I'll explain this better if you still have questions on it when I get back. And then from 3 to 4 it's positive, so it stays at it as is. So to summarize, when you have absolute values, you're going to have to evaluate and figure out when is that curve underneath the x-axis. When it's underneath the x-axis, or meaning when the integrand is negative, you're going to have to make sure you take the opposite right there. Okay? And again, that's all dealing with the absolute value. Tricky question. Okay, so from here, then I do, boy, I've got 3 parts. I have to do the antiderivative of all 3 parts and evaluate them differently, from the first one from 0 to 1, the second one from 1 to 3, and the last one from 3 to 4. Now make sure that the middle one is being subtracted. And then I'll just take this away and you can just, here's all the work. Get rid of that. Okay, now within those parentheses, remember you got to take the top number when you substitute it in minus the bottom number. And you'll see me do that within the brackets. See this right here? Here's the top number minus the bottom number. Within the next set of brackets, I'm looking at the middle set of brackets, there's the top number minus the bottom number. The last set of brackets, there's the top number minus the bottom number. And so we get a final answer of 4. All that to get a final answer of 4. Okay, finding that definite integral. Area between the curve and the x-axis. Okay, example 5. Again, pause whenever you need. I'm ready for example 5. Example 5 says to find the area of the region bounded by the graphs of the equations y is equal to negative x squared plus 3x and y is equal to 0. And if you look here, it's not telling me any more than that. Every problem that we've had so far has been set up for us, and it tells us what the boundaries are that we need to find the antiderivative between. So what we need to do is we need to set these equal to each other. I set 0 equal to negative x squared plus 3x, and I solve. I get x to be 0 and 3. That tells me, boom, right there, what do I need to, how I need to set up my problem. I have the integral from 0 to 3. My integrand is negative x squared plus 3x, and we're finding the integral with respect to x. Okay, so there's my antiderivative, and there's my whole problem. Okay, final answer on that one is 9/2. So on that one, you just, if it's bounded by the graphs of the equations, you set those equations equal to each other to see where they intersect. And that's what it's bounded between. Okay, so make sure on this first section that you've read all the boxes, you understand what the fundamental theorem of calculus is stating, and you know, all the nice little bullet points that I've put in there. The mean value theorem for integrals is what's coming up next. Let me add in a page here because I don't have a sketch here. If I am trying to find, just real quick, the area between the curve and the, let's say the x-axis. If I look at the first one, if I inscribe on the inside here a rectangle and finding the area of the rectangle, where this is f of m, and you can see the diagram on your notes really well. and this is A and this is B. And I can approximate that area, f of m dx, going from A to B, to be approximately, or to be equal to f of m, which is my y value, times my x value, which is b minus a. Okay? And in this, if you think about this, won't this right here, this area, be less than the area under this curve right here, the blue curve? And that answer is yes. Okay, so here I have f of m times b minus a. That is going to be less than my integral from a to b of f of x dx. Okay? Now, the one on the end, on the far right side on the notes, has hopefully the same curve, so I'm going to try and draw the same one. But in this one, I'm going to take and circumscribe. That means put the rectangle on the outside. Okay? So if I look at this one, where I have, again, a to b, the integral from a to b, we're going to call this height here f of capital M, f of m dx. And I'm going to say, well, that's going to be equal to f of m times b minus a. Well, if I look at that, that's not really a really good estimate, because in this case, f of capital M times b minus a is going to be larger than my integral from a to b. You with me on that? Okay, so the mean value theorem for integrals basically is telling you that there is some value. Let me sketch something real quick here. Trying to get the same curve here. There's some value in here, c, such that it's kind of like the mean value theorem that we had earlier, such that the integral from a to b of f of x dx is equal to f of c times b minus a. There's some value c such that those two will be equal to each other. And that's what the mean value theorem for integrals is stating. Okay, so looking at example 6. Let me get caught up here on my notes. I know I'm going fast, but you can pause. Okay, example 6. Find the value of c guaranteed by the mean value theorem for integrals for the function f of x equal to cosine of x over the interval between negative pi over 3 and pi over 3. Now, it might be helpful at one point in time to know what negative pi over 3 and pi over 3 are in decimal form. So in decimal form, I'm just going to put them in here real quick. That is negative 1.047 to 1.047. Might be helpful to know that here pretty soon. Okay, so what I'm looking at first of all is there is my mean value theorem for integrals, and that's what I'm trying to find. That's just restating the formula. Now let's make it apply to this problem. So what I have is in red here the integral from pi over 3 to negative pi over 3 of cosine of x dx, and that's the f of x equation that they gave us. And I know that that's going to be equal to cosine of c, that's my f of c, times the quantity, and that would be my b minus a, my pi over 3 minus a negative pi over 3. So just setting that up and plugging it straight into my mean value theorem formula. So I'm going to work the left side and the right side kind of independently and see what I can come up with. On the left side, the antiderivative of cosine is sine. I'm going to evaluate that from pi over 3 to negative pi over 3. On the right side, I just have cosine of c times 2 times pi over 3. And here is the rest of my work. Now again, I'm working the left side independently than the right side. The left side I'm going to evaluate sine of pi over 3 minus sine of negative pi over 3. So on the left side that simplifies down to radical 3. I'm looking right here. On the right side I just kind of bring that down. So looking at the red arrows, I have radical 3 is equal to 2 pi over 3 times cosine of c. And then I just need to solve for c. So I multiply both sides by the reciprocal of 2 pi over 3, and then I do the inverse cosine. So if I look at that, I have c to be two values. I get 0.597, and remember that cosine is going to be positive in two quadrants. Quadrant 1 and quadrant 4. Now, since I'm going from negative pi over 3 to pi over 3, I'm going to take my quadrant 4 angle and write that as a negative 0.597. And again, this is in radians. Okay? Wow, a lot of notes for a day that I'm gone. I'm trying to move along here. Average value. You have a nice little diagram in your notes to understand what an average value is. If f is integrable on the closed interval from a to b, then the average value of f on the interval is 1 over b minus a times the integral from a to b of f of x dx. Okay? And basically what you're doing is if you take your mean value theorem, let's see if I have that written down here. No. Take your mean value theorem for integrals and solve for f of c, and that's basically what you'd have. So I think that's written there on your notes as one of the bullet points. Alright, so f of c from the mean value theorem f of c from the mean value theorem is called the average value of f from a to b. Okay. Example 7. Find the average value, and here is the first problem. And I have f of x is equal to x squared plus 1 all over x squared. And I am going to split that up. I'm going to write that as, think of this as x squared over x squared plus 1 over x squared. Okay, that's what I'm working on right there, which is the same as 1 plus x to the negative first power. Much easier to work with 1 plus x to the negative first power. Or, I'm sorry, 1 plus x to the negative second power. Okay, and I'm going from 1/2 to 2. So I set up, there's my generic average value formula. Then I put in my information. I have 1 over b minus a, so that's going to be 2 minus 1/2 in that denominator. I'm evaluating from my lower bound of 1/2 to the upper bound of 2. And my integrand is 1 plus x to the negative second with respect to x. So basically I do everything the same. At the very end I'm going to just multiply by that 2/3 out front. Right here I get 1 over 2 minus 1/2 is 1 over 3/2, so I flip it and multiply to get 2/3. And then I just do my integral, and I'm going to leave you to copy all that down, or just kind of do it yourself if you want to, and then check with my answer up here in a minute. So go ahead and pause while we copy that down. And the final answer I get is 2. So a lot of work to do on that one. Part B on this one says to find, oh no, where's part B? Here's part B, went to the wrong page. Part B says to find all values x in the interval for which the function equals its average value. So 2 is our average value, and I go back to my original of x squared plus 1 all over x squared. And basically I'm just going to solve for x. So I cross multiply, solve for x, and I get x to be plus or minus 1. But why do I not use negative 1? Well, hopefully you found that out. Is negative 1 in my restricted domain? And the answer is no. X equal to 1, that's the only one that's in the interval listed, 1/2 to 2. Alrighty, so that's all we had to do for part B. Fundamental theorem of calculus, the second version. Okay, I call it kind of the duh theorem. Okay, but here's why. If I take the derivative of an integral, I basically get f of x. I'm kind of undoing what I just did. The derivative undoes an integral, or the antiderivative. So if you look here, I'm just plugging in my x. Well, that works most of the time. Let's look at example 8. Kind of go through a couple of examples here. I'll kind of show you why it works. Here's number 8. I have f of x equal to the integral from 1 to x of the fourth root of t. So I'm going to rewrite that as t to the 1/4 power dt. And I need to find the derivative of that. Okay, so let's do the integral. Let's go from 1 to x of t to the 1/4 dt, and let's evaluate that first of all. Let me just kind of show you what I get when I evaluate that. And I still have that d dx, that derivative sign right there hanging out front. So I get 4/5 t to the 5/4, evaluating from 1 to x. So I plug in the x first. X just goes in for t. Notice, boom, right there, x goes in for t. And 1 goes in for t the second time. So I have 4/5 x to the 5/4 minus 4/5. And then I just need to find the derivative. So once I get to this part right here, I've done my antiderivative, I've done my evaluation of that definite integral. Now I do the derivative of that, and look where I'm at. I'm back to x to the 1/4. Now, what was my, look at the beginning. It was, look right here, boom, t to the 1/4. So what's the difference between those two? Well, the t has become the x value that's up there. Okay, that's what's happened. So if I look at part B, I have something different on part B. If I look at this one, I'm going from 2 to x squared. Okay, so if I go through and actually do my antiderivative and evaluate this part right here, showing my work, I get 1 over negative 2t squared, and now I substitute in t squared, or x squared and 2, and that's what I get. Okay, that's just doing the antiderivative and then plugging in my my restricted domain there from 2 to x squared, or my interval that I'm looking at. So then I look and I say, okay, now I'm going to do the derivative of that. So if I do the derivative, let me just get rid of all this. Here's what I got, 2x to the negative fifth. Now 2x to the negative fifth, let's compare it to what we had before. That is not x to the negative fifth. Okay, so I can't just plug in an x on this one, but here's the shortcut. To find what I'm doing here is I just plug in my upper bound of my limit, and then I multiply by the derivative of that upper bound of the limit. Now this only works if the lower bound is a constant. Now did everybody hear me say that? This only works when the lower bound is a constant, but I'd say most of the time it usually is. So if you look here, there's my shortcut. I get 2x to the negative fifth. So when you're doing these problems, just remember, let's see if I have my last one here. My shortcut is just to take this exponent for part C, plug it in for my variable in my integrand, so I have sine x squared squared. Now I take the derivative right here, that's the derivative of that upper bound, which is 2x. And that came out front, and boom, there it is. Okay, this was very quick, I know, and hopefully you've paused it some. And I know it's boring to sit there and for 30 minutes, and it's probably longer than that since you had to pause it. We'll go over all questions next time, and you have homework to work on, and work together and do the best you can on figuring out Section 4.4, Fundamental Theorem of Calculus. We'll continue with the Fundamental Theorem of Calculus next class period. Hope you have a great day.